Hello friends. So far we have seen testing and testing techniques. Now in this session we will see the type of testing. So today we are going to discuss black box testing. As we have seen, good test case design is the key to suitable testing. The goal while testing is to detect the most of the defects through a small set of test cases. Due to this basic goal, it is important to select the test cases carefully. Best are those test cases that have a high probability of detecting a defect if it exists, and also whose execution will give a confidence that no failures during testing implies that there are few defects in the software. There are two basic approaches to designing the test cases: black box and white box. In black box testing, the structure of the program is not considered. Test cases are decided solely on the basis of the requirements or specification of the program or module, and the internals of the module or program are not considered for the selection of a test case. In black box testing, the tester only knows the inputs that can be given to the system and what output the system should give. In other words, the basis for deciding test cases is the requirement or specification of the system or module. This form of a testing is also called as functional or behavioral testing. For selecting test case, there are no formal rules for designing a test case for a functional or black box testing. However, there are number of techniques that can be used to select test cases that have been found to be very successful in detecting the errors. So, let's see some techniques which we can use for selecting the test cases for black box testing. First one is equivalence class partitioning. Because we cannot do exhaustive testing, the next natural approach is to divide the input domain into the set of equivalence class, so that if the program works correctly for a value, then it will work correctly for all other values in that class. If we can indeed identify such a classes, then testing the program with one value from each equivalence class is equivalent. However, without looking at the internal structure of the program, it is impossible to determine such ideal equivalence classes. The equivalence class partitioning method tries to approximate this ideal. An equivalence class is formed of the inputs for which the behavior of the system is specified or expected to be similar. Each group of inputs for which the behavior is expected to be different from the other is considered a separate equivalence class. So let's see the example. Here we are having one parameter called age, which accepts the value from 18 to 16. It is expected behavior of a age parameter. So we can partition the input values into the three different classes. First one is the values which are less than or equal to 17. That will be the invalid values. Next one is 18 to 60, which will the valid values. And the third and last class is greater than equal to 61. So if we test any single value from this class, then this testing is sufficient for that entire class, because if one value gets failed in that class, all other values will definitely get failed. If one value will succeed in particular class, then all other values inside your equivalence class will be succeeded or will be validated. Now let's see the next technique: boundary value analysis. It has been observed that programs that works correctly for a set of values in the equivalence class fail on some special values. These values often lie on the boundary of an equivalence class. Test cases that have a values on the boundaries of an equivalence class are therefore likely to be a high yield test cases. And selecting such a test cases is the aim of a boundary value analysis. In boundary value analysis, we choose an input for a test case from an equivalence class such that the input lies at the edge of an equivalence class. Boundary value for each equivalent class, including the equivalence class of the output, should be covered. Boundary value test cases are also called as extreme cases. Hence, we can say that a boundary value test case is the set of input data that lies on the edge or boundary. So let's see the example. We are having the same example as previous. Here, age is a parameter which accepts the values between 18 to 56. So, in boundary value analysis, we will partition the values or inputs into three different classes. The first class is minimum minus 1. So our minimum value of a age is 18. So 18 minus 1 is 17. So we will check the value 17 which lies on the boundary, whether it is a valid or invalid. The next class is the values which are valid and which lies on the boundary. For example, minimum value 18, minimum plus 1 value that is 19, maximum value minus 1 that is 55, and maximum value 56. So these are all four values which lies on the boundary and which are in the valid case. And the last class is maximum plus 1 that is 56 plus 1 is 57. So in boundary value analysis, testing or test cases will be selected based on the boundary inputs values. Now let's see the next technique. Pairwise testing. There are generally many parameters that determine the behavior of a software system. So, not necessary you can pass one single parameter, but sometimes you have to pass the many parameters to the system. These parameters could be direct input to the software or implicit settings like those for a devices. These parameters can take a different values, and for some of them the software may not work correctly. Many of the defects in the software generally involve one condition that is some special value of one of the parameters. Such a defect is called as a single mode fault. The objective of pairwise testing is to have a set of test cases that covers all the pairs. Now let's see the example. In here, we are having 8 test cases in a first table. So, x, y, z are the parameters and t1 to t8 are the 8 test cases. X, y, z parameters are having a different values in different test cases. So, if you look carefully, we can reduce these 8 test cases to the 4 test cases according to the pairwise testing. Let's see the test case T1. It is having the input values A, C and E. So we can eliminate the test case T2 because we can cover all the inputs of T2 and T3 using T1 and T4. Similar way, we can reduce T4, T5 and T8 as well. So the 4 test cases, that is T1, T4 and T6 and T7, will cover all your inputs in pairwise manner. That is the combination. So the basic aim of pairwise testing is to cover all the sets of possible pairs for a testing. Now let's see the next technique. State-based testing. There are some systems that are essentially stateless in that for the same inputs, they always give the same outputs. Many batch processing systems, computational systems, and servers fall in this category. There are, however, many systems whose behavior is state based, in that for identical inputs they behave differently at different times and may produce different outputs. The reason for different behavior is that the state of the system may be different. In other words, the behavior and outputs of the system depend not only on the inputs provided but also on the state of a system. The state of the system depends on the past inputs the system has received. A state model for a system has four components. First one is a state, represents the impact of the past inputs to the system. Second, transitions, represents how the state of the system changes from one state to another in response to some events. Events, input to the systems. Last, actions. The outputs for the events are nothing but the actions. The state model shows what state transitions occur and what actions are performed in the system in response to events. Now let's see the example. Suppose we have to design and build a simple system for taking an online survey of a students on a campus. There is a set of multiple choice questions and the proposed system will provide the survey form to the students who can fill and submit it online. We also want that when the user submits the form, he or she is also shown the current result of the survey. That is, what percentage of students so far have filled which option for the different questions. Now suppose we want the system to be extended in a different way. It was found that the database server is somewhat unreliable and is frequently down. It was also found that when the students is give the result of the survey, when he submits the form, somewhat outdated result is acceptable as the results are really statistical data and a little inaccuracy will not matter. We assume that the survey result can be outdated by about 5 data points. So now the dean wanted was to make the system more reliable and provide some facility for completing the survey even when the database is down. To make the system more reliable, the following strategy was proposed. When the student submits the survey, the server interacts with the database as it will. The results of the survey, however, are stored in the cache by the server. If the database is down or unavailable, the survey data is stored locally in the cache component and the result saved in the cache component is used to provide the result to the students. This can be done for up to 5 requests, after which the survey cannot be completed. To create a state machine model of this system, we notice that a series of 6 requests, the first 5 may be treated differently. Hence, we divide it into the two states. One representing the receiving of 1 to 4 requests, that is the state 1, and the other representing the receiving of request 5, that is the state 2. Next, we see that the database can be up or down and it can go down if any of these two states. However, the behavior of a request if the database is down may be different. Hence, we create another pair of states, states 3 and 4. Once the database has failed, then the first 5 requests are survived using old data. When a request is received after receiving a 5 request, the system will be failed, that is in the state 5, in which it does not give any response. When the system recovers from the failed state, it must update its cache immediately, hence it goes to the state 2. The state model for this system is as shown in the figure. I represents an input from the user for taking the survey. Note that we are assuming that the state model of the system can be created from its specification or design. This is how most state modeling is done, and that is how the model was built in the example. Given a state model of a system is a one thing, but how should test cases to be generated for a state model? Many coverage criteria have been proposed. We discuss only few here. Suppose set of a test cases is a T. Some of the criteria are all transaction coverage AT. In this, T must ensure that every transition in the state graph is exercised. Second, all transition pair coverage ATP. In this, T must execute all the pairs of adjacent transactions. An adjacent transaction pair comprise two transition, an incoming transition to the state and an outgoing transition from the state. Third, transition tree coverage TT. In this, T must execute all simple paths where a simple path is one which starts from the start state and reaches a state that it has already visited in this path or a final state. These are the four techniques. Now, there are some special cases as well. It has been seen that programs often produce incorrect behavior when inputs from some special cases. The reason is that in the program, some combinations of inputs need a special treatment, and providing a proper handling for these special cases is easily overlooked. For example, in arithmetic routine, if there is a division and the divisor is 0, some special action has to be taken, which could easily be forgotten by the programmer. These special cases form particularly a good test cases, which can reveal errors that will usually not be detected by the other test cases. Special cases will often depend on the data, structures, and the function of the module. There are no rules to determine the special cases, and the tester has to use his intuition and experience to identify such a test cases. So, this is all about the black box testing and techniques. If you are having any doubts, please feel free to drop your queries under the discussion forum created in software engineering subject on your Moodle. Thank you for listening.